The last video showed us how we can check up on processes using top, see all the running processes and the ones that are taking the most amount of CPU. We can also look at the details of each process using the ps command, and there's a number of different options. You can use all or just one of these or none of these, ps or ps minus a, or you can add on e, f, x, and so on. And we'll take a look at all of these in a little bit more detail, but mostly we'll be looking at the /proc file system, which is a window into the kernel data structures that have to do with processes and other things. So we'll take a simple example, and maybe we'll look at an actual system too, a Linux system. And I should point out, although these two things are available on most Unix systems, /proc is something that's unique to Linux. Okay. So suppose we have we have a system where we're running the program vi, and we're executing vi on file.c. So, and there might be more than one process or more than one user using the same program. So, for example, let's say we look at the current situation using the top command. You see something like this. You might see a process ID for the top command itself. So this is top, showing you all of the programs running, and one of those programs is top itself. And so top basically shows you that top is running. Here's the status. It has a certain process ID, certain user. Let's say that's the user, certain priority, and so on. Okay, and it's just one of many programs that's running. So you can see this on any Linux system. Remember, if top is running, if you're not sure how to get out of it, press the Q button and you'll get out of top. PS just lists the current status of all the processes, or actually depending on what options you use. If you use A, E, F, X, that's pretty much all the options. There's actually more, but these are the main ones. If you list all of these, you'll see pretty exhaustive list of everything that's currently running. So for example, this is a remote system. So the SSH daemon started up another copy of SSH daemon, which responded to a remote login and ran bash. And bash is a shell which started up vi. So if you're running vi, vi is running sort of under bash, which is running under the SSH daemon, and so on. Okay. So, and also you might have two shells, like in this case there's two bash shells running. The second bash shell is executing this command itself, which CPU info contains information about the CPU. You can cd to any one of these folders, even if they don't belong to you, and you can see all kinds of information about processes. So each one of these folders, so these are all folders that whose names are just numbers. And these are the process IDs of the programs that are currently running. So for example, oops, let me go back up. There should be a file for 17982, which corresponds to the VI program running. If you look in here, 17982, here it is. And you can cd into it. So to do this, you'd have to have two windows, one in which you run vi, and another in which you can list out the output of ps to find out the process ID of the vi command, and then cd to /proc. You should be able to find that process ID. Of course, yours will be different. And then you can cd into it, do an ls-l. It'll give you a bunch of information about this process. One of the commands you can use to print out some of these files is od, octal dump. So the od command just prints out character by character, in this case using -c option, the command line. And this shows you that the command line is a bunch of strings, null terminated. So you see vi, null termination, file.c, null termination. So what is this telling you? This is just telling you that the way this process was started up was through a command line, and the command line arguments were vi, file.c, and sure enough, that's how we started up this process. We said vi file.c, and you see all those things show up in this command line file. So let me just back up. This is where right now we're looking in /proc. We're looking in /proc/ a particular directory that corresponds to a process that we're currently running. If you do an ls -l, one thing you might want to notice here is that all of these files supposedly have a file size of 0. Why is that? Because these are not real files. This is just a pseudo file system that exposes Linux kernel data structures as a file system. So they don't take up any space. They're just a way of representing kernel information. Okay. Oops. So we ran vi file.c. We used top, and we actually it'd be hard to see that unless that vi command took a lot of time. It's so low in CPU usage that it probably won't show up in your window. That's okay. You can use the ps command and see that here's our vi command. Its process ID is, in this case, it was 17982. cd to /proc. You'll see 17982 there, or whatever yours is, whatever process ID your vi is. You can cd into there and find more details. You can cat the contents of a file or do an octal dump. And you can cat, for example, environ. This has a list of all the environment variables, shell environment variables that are currently defined for this process. And you inherit all of this from bash. You can cat maps, and this is how I construct those maps of the Linux process space. So let me just back up quite a few slides. The way I construct these is by using the maps file or pseudo file for processes. So I jump to a certain, you should be able to see the correspondence between the output of maps and those diagrams that I've drawn. So for example, here is all the text that is the actual executable, vi executable loaded into memory, starts at about 080000, roughly speaking. Then there's all these shared libraries, and then way down here is the stack. It doesn't tell you that it's a stack, but that's, roughly speaking, that's where the stack is. Okay. There's another file in the process in the directory for the process for vi. I can cat a file called status. Tells us that the name of the file is vi. It's sleeping, that is, it's not running right now, because the program that's running right now is the cat program. When this is all listed, it's the cat program that was running and listing all of this. Here's a process ID, thread group ID, parent process ID, and so on. If you take a look at this parent process ID, I'll scroll back. It should make sense because vi was started in a bash shell. Which shell? Here's the parent process ID, 17954. And so when you look at the parent process ID, that's the thing that you should see, 17954. Okay, and there's a whole lot of other information, some of it useful, some of it maybe not so useful, but these I just wanted you to get a rough idea. I'm not going to explain every single one. There's a ton of information here. Let's just take a quick look at environment variables. So remember that you can set environment variables in a shell. So if you were to say, for example, run the env command and pipe the output to a grep command to search for something like CS248, you will see nothing. If you set a variable CS248 equal to hello, and then I think you need a semicolon here or something, and then do an environment colon grep CS248, you will see that this variable was defined in this environment. So let's just try that. Let's take a quick look at this. Should be doable. So I'll cd somewhere to my home directory and do env. There's a whole lot of stuff. Let me just check if CS248 is one of them. Nothing. Okay, so if I say CS248 is equal to hello, And then let me see if I can get by without using a semicolon. env grep cs248. What does this tell you? Oh yeah, it works. So I didn't need a semicolon here. It just treats it as a separate command. Good. A semicolon would also work. Oops, I guess not. I guess you need to have no semicolon. I was guessing that you needed it and I had a typo, but you don't want the semicolon. This works. So this tells us I set up this variable called cs248, and I check the environment, search for cs248, and cs248 was defined to be hello, which is something I did right there. If you do this again without defining it, what you'll see is that there is no variable anymore. So that variable only existed for basically for this line. Okay, so you define it, and right after you define it, it's there, but very next line of very next command, it's gone. That's how environment variables work, unless you export them. So you can do this. You can say, so if you define this momentarily here, or for just temporarily, and you search for it, it's there. But then if you search for it again, it's not there. You can define the variable cs248 to be hello, and then export it. Once you export it, then it's persistent. It stays in your shell, and then it's now part of this particular shell. Of course, as soon as you exit from the shell, start up another shell, this is gone. There is no variable, but for the duration of the rest of the duration of this shell, if you do env and grep for cs248, it'll be there. Okay, so that's how environment works, and you can access all of this quote-unquote programmatically. That is, you can access the environment from within a C program. It's just like you can have an array of strings as an argument to your main. Environ is also an array of strings. So when you see car star, remember you want to think that's a string. If you see car star star, chances are good that it's not just a pointer to a single character, but an array of strings. Okay, and then if you define this to be an external variable, that is an external and global variable, then you can use it. And you can say environment, basically get each string. So car star e is just a string. Getting a pointer to the first location of environ, first array location environ, printing it out, bump up environ, that is you're looking at the next array location, and so on, printing it out. And this will basically list all of the environment variables. So try this out. Set up a program like this, and what it should do is print out exactly the same information as the env command. So just like env prints out a ton of information, that's all the environment variables. You should be able to see all of this from within a C program if you ever need to do it. Okay, a program like this would do it. You can also get a string corresponding to a single environment variable, like for example cs48, using the getEnv function. You have to do a #include stdlib, and then inside your main you can use getEnv. So getEnv, you can look at the man page. You need something like this #include stdlib.h. It takes a constant string, C-style string, as a parameter, and you can use, for example, this, and this will return the value of cs248. If we still had the same definition that we had before, this should return, string should be hello, because that's what we set cs248 to. Okay, so let's take a break here, and we'll continue with this in the next video.